Hello everyone, welcome back to the course. Today we will see deep learning. In recent years, deep learning is a famous word, especially in AI, artificial intelligence. But what is deep learning and what can it do for AI or for our life? We use the game for our example, so we will see what deep learning does in game. When you use deep learning in game, we call game AI, and the game AI has two meanings. One means AI plays game, and another means human play game. And in the left, AI plays game, that means AI will like human being, it play the game like Mario. And human play game, that means the AI will be our partner or be our enemy, it will fight with us. Okay, and let me see the AI plays game first. We will see how AI play Mario. For example, we use this for MCTS Super Mario AI. Okay, in this video we can see AI control Mario to jump or to eat the coin or to touch the enemies. And you can see this curve. This curve, that means AI think what will Mario do next in the next steps. And it also calculate where is the enemy and where is the object, and Mario need to do something like jump or go left or go right. And you can see here are some information for Mario and for AI. AI can count of this, and it can know how will it next or the behavior. And you can see in this video, you can see Mario follows the curve, and if there are any change, the curve will be changed. And you can see this curve are dynamically calculated and modified in each frame. Okay, and this is our first example. Maybe you think deep learning is very huge and very strong, and to do this, or can deep learning play Mario in the beginning, and this is very strange and powerful to let Mario won't die? The answer is the deep learning is very stupid in the beginning, and it used try and error and die, and then collect a lot of information, a lot of data, and a lot of result, and then it will know how it will change his behavior, and then the Mario won't die. So we see another video to see the AI play Mario in the beginning. We can see this video. And all video we see in this class, I have put it to the slides. For example, if you want to know each of video, you just see my slide and there are the links here. You can see the link for detail, or you can see the whole videos. Okay? And then we see the second example. When AI plays with Mario's in the beginning, you can see the AI is very stupid, and then he will get more smarter and smarter. Okay, you can see here, this is the behavior for a Mario, like walk or jump. And you see the first time, the AI is don't know what he will do, so the Mario is always here, and doesn't go right and doesn't jump. Okay, and after many rounds, AI knows what will he do, and Mario won't die. Okay, you can see this. After 24 minutes, about a half of hour, AI knows, oh, I control Mario to do this, and Mario can go to right and don't die. So you can see that AI is used try and error and correct a lot of information, and then to distinguish what it can do or what it works is better. So this tells us if we do something, we can use AI's behavior or AI's math idea to do the same. We just try and feedback and fix our doing way, and then we can get successful. Okay, you can see that if the question or the problem is harder, the AI will take more time to learn and get the efficiency way to solve the problem or take a issue and very close to the real solution. Okay, and this is a Mario AI. In the beginning, it is from very stupid to smarter, and if the game is more and more difficult, and the AI will take more time to find the experience and find the solution. For example, another Mario, because Mario has a lot of generation, so we see this generation to see how AI solve the problem to play the Mario in this generation.
Welcome back, Seth Bling here. You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mar.io. This program started out knowing absolutely nothing about Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called neuroevolution. In this video, I want to teach you about how Mar.io learned to beat this level, Donut Plains 1, what its brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mar.io's brain. Let's play it again, but this time we'll look at Mar.io's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll help break it down for you. This structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior. With enough computational power, a neural network could come close to simulating a real human brain, but modern technology isn't there yet. On the left side you have the inputs. This is what Mar.io sees. It's a simplified view of the level. The white squares stand for blocks the player can stand on, and the black squares stand for moving objects like enemies or mushrooms. On the right side you have the outputs. These are the 8 buttons that Mar.io is able to press by using its neural network. In between the inputs and the outputs, all those lines and boxes, those are the neural network. Each free-floating box is called a neuron, and the lines connecting those boxes are like the axons and dendrites in a human brain. At any given time, only some of these neurons and connections are actually being used, and this is what people talk about when they say you only use 10% of your brain. The neural network you're seeing is a pretty complicated one, and it got so complicated as a result of a 24-hour evolutionary learning session. So, to explain how neural networks work, let's rewind about 24 hours and look at how the whole process started. This is what Mar.io looked like at the beginning of its training session, all the way back in generation number 0. The program is probably even dumber than you thought at this point. Often it just stands there and doesn't even press any buttons. If Mar.io stands still for too long, it'll cut off a simulation and try the next neural network, so it's mostly just jumping from one simulation to the next. But occasionally, the neural network says to press the right button, and the player starts walking right. Behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network to understand just how that works. This is one of the randomly generated neural networks that appeared in the first generation of the simulation. There are some green lines and a red line, and one neuron in the middle. Here's how it works. A green line is a positive connection, and a red line is a negative connection. A green line reading from a black or white square will turn its output the same color. A red line reading from a black or white square will turn its output the opposite color. In this case, the green lines read from the platform that the player is standing on and make the neural network press the right button as long as the player is standing on it. However, when the red line reads a black square representing one of those caped Koopas, it presses the A button and makes the player jump. This puts the player in a position where the green lines are no longer reading a white square, so the right button turns off and Mario just stands there. This is a really basic example that illustrates how a more complicated neural network might operate. The more lines and neurons you have, the more nuanced the decisions can be. So, how exactly do we get those more complicated neural networks?
Okay, we stop here, and the left part you can see by yourself. Okay? And we can see in this generation, Mario has a lot of buttons and a lot of direction it can do. So AI in this Mario generation is need to be more smarter and than before, because in the old generation they are only right and jump, or right and jump. So you can see when the game is very difficult, and AI will need to be more smarter. Okay. And here is the AI plays game, and then we see the human plays game with AI, and there are two videos here. We just saw quickly for the first one and see another one for detail. Okay. And this one is use the MCTS to let the AI think what is his next. The MCTS, that means maintain carrier tree search, and it is for a tree search, and you can see this as this video, and we will see the part of MCTS.
Understand why it is more advanced, we should compare it to Minimax, which is what Deep Blue used to defeat the top chess player in '96. First, some similarities. Both Minimax and Monte Carlo Tree Search uses both of them use game trees, which are directed graphs that represent all possible moves and positions in a game.
Okay, in this one, you will see the computer will need to know all possible paths in this game. So for the Dick Circle game, and you can see the tic-tac-toe game, you can see that the computer needs all possible paths, and then he delete the impossible paths when the player after player did the action.
Think of game trees as just like any normal search tree, except the nodes represent game states. So let's say this is tic-tac-toe. If I put my X in this corner here, then the game state changes to be this node. If my opponent places his circle here, then the game state would change to be at this node. Different nodes lead to different moves being available as child nodes, just like in real life, where different decisions can affect future possibilities and what future possibilities are. The leaf nodes, they represent win or loss or a tie. Okay. Now, I don't really have much time to review Minimax, but long story short, it searches through the entire game tree or many steps ahead, uses an evaluation function to determine what future positions are favorable or unfavorable, and then assuming the opponent chooses the best possible move for himself, it will then act accordingly to put itself in the best possible position for victory. Key thing to take away is that it looks through this entire thing, every single branch, every node, and determines the best choice. If the tree is too large, then it would take way too long to do all its calculations for the whole tree, so it would limit search to all the possible positions up to a certain depth, represented by one of these lines. The bigger and more complex the tree is, the fewer turns it is able to look ahead, and basically the more stupid it becomes. Obviously, this is a problem if the problem is too complex and there are just too many possibilities. Let's say a problem is so complex that Minimax can only look one step ahead, right? Like just this next move. In that case, the AI pretty much becomes just useless. Another issue with Minimax is that if the game is so complex that you cannot write a good evaluation function to tell the AI what is a good or bad position.
Okay, we skip this part and we see the MCTS part. Let me find this here.
The question is, how could the MCTS, how could it actually plan or think ahead in a situation where there are just so many potential moves and counter moves to possibly evaluate all nodes, even with a limited depth search? The way the MCTS does it is by creating an asymmetric stats tree which detail the value of each position and adapts to the topology of the game tree. The algorithm visits more interesting nodes more often to focus its search time on the more relevant parts of the tree. And the way it sets and updates these nodes is by running simulations which start out as random and later become less so. So don't worry, I'll go through what all this means step by step. Let's say this is a hypothetical game tree for Go. All these nodes represent positions or game states. The top node here represents the board at the start of the game, so the board is empty here. And these 3 nodes represent the first, the opening move that you can make. Obviously, the game of Go, 19 by 19, so there's going to be more than 3 opening moves, but let's just pretend it's true. Let's just pretend it's just 3. So yeah, how does an AI know which move to make? It will start, the Monte Carlo tree search will start by making its stats tree at the starting point, which is this one right here. And it will call one of these for functions, selection, expansion, simulation, update, depending on the situation. Here, there are child nodes that it has not explored yet, so it will add a new node to the stats tree that represents the position the AI will investigate. This is the expansion phase. It will then, from that position, basically run simulations for, it will make random moves for itself and its opponent until it reaches the end, which can either be a win or a loss. And then it would call update, which updates the value of this node that it ran the simulation from. So here it would be a 1 win out of 1 simulation. It will then do that same thing for the next 2 nodes. And at this moment, the numbers say the left node is the better move, but chances are we don't really know that's true. The numbers don't really mean anything at this point because the sample size is too small.
Okay, and we stop here. And the computer will count this again and again, and it will get the potential move with the last win chance, the last chance with win. Okay, and so this is MCTS idea. And for some games, it doesn't use MCTS. It uses a finite state machine. That means the controller or the programmer have defined some statement, and then the computer will see the situation and change its statement and make the players or the enemy sees it is like the real human do. Okay, we see another video here.
Hey guys, today we're going to talk about the fundamentals behind strategic AI systems in games. Even if you have no idea how to code and have no intention of learning, we'll look at some basic AI frameworks, how they're built, and how they may affect a game's design. We'll also learn how to code them from scratch in the next video, but first, let's get started. So a game's AI is what makes it feel alive. It makes us feel like we're facing coordinated squads and fearsome monsters. In the past, the AI was limited to simple programming, like if player in range, attack, otherwise walk left and right. Though plenty of great games only require this simple logic to work. The challenge came from how different enemies attacked and moved with this logic. Did they move towards the player quickly or slowly? Did they fly? Did they go in a straight line or dart around the map? Do they have a ranged attack or melee? Some may follow a hard-coded pattern like hide, hide, hit, or block, hit, block. But this complexity of logic works fine for many action games and platformers all the way back from the
Okay, we skip it here to the finite state machine figure here.
And I know I have an audience with all different skill levels, but I give you the Happy Cat guarantee you will learn something new from those notes. They're really a great resource on algorithms. Anyway, whether you've studied it or not, a finite state machine is basically a bunch of nodes or states with transitions between them. In our case, our states are what our enemy is doing, their actions, like attack, block, or do nothing, stay idle. So let's say we start off idle, we're doing nothing, and then a player comes in range. This triggers the transition from idle to attacking. And now the player is retaliating our advances, and we notice that the player's state is attacking. So this is the trigger for us to transition from our attack state to our block state. And so while the player remains attacking, we're going to remain blocking and defending. So we can transition from this block state back to itself while we're remaining blocking. With this type of game, you usually want to be able to access any state from any other state. Meaning if we're blocking, we want to be able to go to attacking or do nothing or move to. We want to have those options open, but we have to define a transition and what triggers that transition for every possible combination. So this gets especially messy if we want to add new states or new actions like use potion or cast spell. We have to update the arrows for every possible transition. If you have an enemy AI that just attacks, defends, and does nothing, like our example, a state machine will probably do fine. In fact, think about this. The logic for transitioning between animations is the same for determining actions. So if you have an animation state machine, like in Unity's animator, you can add your collision boxes and damage values and logic to your animated objects and model your simple AI through the animator logic.
Okay, we stop here, and the left part you can see by yourself. And this is the AI does in game, and you can see we call this for the game AI, and 2 minutes AI plays game or human play game with AI. And what is the AI's history and its background? We will see in the next slide, and we will quickly introduce the history of the AI and deep learning. This is the evolution of AI. You can see that in the 1950s to 1970s, this is the AI. The name of AI is appeared, and this is for the making intelligent machine and the program. This is his main idea. And then to the 1980 to 70 years ago, this changed to the machine learning. That means we think AI have ability to learn without being programmed, but this not very useful or not very workable in that time. And then after 14 years, about 2010 to now, the deep learning is short, and it will be learned based by the deep neural network. So in today, a lot of AI in the behind use the deep learning to do the smart thing, like for the how to learn something or how to do something from its experience or from the lot of data set and the database. And the difference between AI, machine learning, and deep learning, you can see like this figure. And although it is all in the artificial intelligence field, but the deep learning is a subset of machine learning, and the machine learning is a subset of the AI. And deep learning focuses on the thing that make the computation of multi-layer neural network feasible, and it can learn by itself. And that means the computer collect or see a lot of data. It can generate his rule by computer itself. And in machine learning, this is to give computer the ability to learn without being inspection program. And that means human need to get some rule or some characteristic to machine learning, and then let the machine learning to learn experience and the rule from the characteristic or given rules. And an artificial is like the name, just want to let the computer do by itself like the human did. And here is the figure that shows the difference between machine learning and the deep learning. We can see in the above figure, if we put in a car and we need to extract the feature from the car, and then we tell the computer, and the computer will see, oh, a car means it has 4 wheels, or it has an engine, or 4 windows, and so on. And these features are given by human, so it all controlled by human. And then we put another figure and let computer distinguish it is a car or not a car. Then the computer will use the feature extracted by human and his rule to distinguish this figure is a car or not a car. So in machine learning, the most important is the feature extraction, and this will depend on this guy. If he give him a wrong feature, the computer will distinguish a wrong answer. This is the machine learning. And in deep learning, we can see that there is no human here. The feature extraction and the classification and all seems to do are by computer itself. And then if you put a lot of car picture to the computer, and maybe computer will extract the feature as the car is blue. If you give computer all cars in blue, and maybe you will get a feature is the car is blue. And then if you get a red car, it will say it is not a car, until it has a lot of data and shows the car has many color. Then it will delete this blue car feature, and then it will update its feature. Maybe like a car, like a small car is like wide maybe 10 feet or high 5 feet, like this one. And this feature will different between humans, and that I means the feature is created by human and the computer are different. Even the training data are same, the extracted feature will be very, very different. Okay, and let me take a look to see what is the machine learning or the deep learning sort idea for them. They want to looking for a function, and we use this for an example, like a speech recognition. We have a function, and then we give him a speech, and then it will recognize a sentence. Or image, you give it a image, and you want to find a function, and it can tell it is this figure is a cat. And like the playing Go, it will know what is the next move with some function. And then dialogue system, when we say hi and he know with a function, it will respond hello. And what is this function, and how can a computer find this function? We see this is we use the image recognition for example, and this is the framework, and this is the idea. Detail you can see some other case for its code, or you can see in GitHub there are a lot of open source. You can see the open source. In image recognition framework, you can see we have a lot of function. We call a set of function like F1, F2, and so on. And then some function will tell you the right answer. For example, F1 see this figure, it will say it is a cat, and F1 see this figure, it will say it is a dog. And this is the correct function. And maybe another function is F2 see the same picture, but it gets you this is a money or monkey, and F2 see this is a snake. So we know this is wrong. Okay, and then in deep learning, each of function we call a model, and we heard the training model or how to train a model. That means we want to find a correct, or the function can give you a correctable data result, or it can give you a result much close to the correct answer. And this is the model, and each model have a different result, or some function will give you part correct or part wrong answer. Okay, and the training data, that means you have a lot of figure or a lot of data, and then you use this module and to see the training data. Like we have a function input, like this is this figure, this is a monkey, and if this function return the right answer monkey, and this for cat and this for dog, and then we will see this is the goodness function to tell you the correct answer. In training data, these are all labeled. That means you have a figure and a corresponding correct answer, so you can know which model or which function will give you that most correct answer to you. It is in the image recognition, and similar to other field or other functions. Okay, and in this case, we can see F1 is better than F2 because F1 gives you the answer is correct. And when we do the training data, and this is with the function input and function output, and we call this is the supervised learning. This is called supervised learning. Okay, and we see after the training data, we found a goodness function, and maybe this function not only one, maybe 2 or 3, and we want to pick a best function. That means we will randomly choose one, and then we can use this chosen function to do my testing data and see if the testing data responds the correct answer, and this will be the best function. And otherwise, if it's not, and we will turn back to choose goodness function again, or to increase our training data and make more testing or more training to get a more goodness function. Okay, and this part we always call this is the training part, and this is the testing part. And this is the framework for the image recognition. And here, when we write the code or we programming the code, we use this for the step 1 to import or set a set of function, and then the second step 2 is to find a goodness function. That means we use the training data to train our module. That means we found the goodness of function, and then the step 3 to pick the best function. Maybe use the random chosen way, or you have another algorithm to choose the best function from your goodness functions. Okay. We see the one example, and this is the famous example. It will detail and distinguish what you write with your number from 0 to 9. And that means if you write a number here, like the 2, and then it will go to a computer or AI or deep learning, it will tell this number is 2. We will see it for our first example. Okay, this is the input image, and we suppose this is 16 plus 16 pixel, and then we can use this pixel from here to here, left tab to right button, and let them into a lot of input, like S1, S2 to X2056, like this one. And if your number is cover the pixel, and this will be 1, and the empty or the white, and this will be 0. Yeah, the ink. Okay, and each dimension represent a condition of a digit, and we will see this. And our output is for the number 1 to 9, 0 to 9. Sorry, and we can use this for this Y1 to Y10, or you can use Y0 to Y9. It depends on you. And this is like 1, 2, and 9 to 0. And then we calculate it by deep learning or the computer or AI, and we will get the percentage to each number, and the sum of this percentage will be 1, and because this is calculated by our input, and we will choose the highest percentage, like 0.7. This is highest one in the output, so we think this has a very highest possibility to 2. So the AI will think this figure will be 2. Okay, and this example is famous. We call the handwrite digit recognition. So if you use this keyword to search in the search engine, you will see a lot of case or a lot of explanation in the network. Okay, we will see this in a PowerPoint animation. Okay, here this is our input S1 to S256, and the output is 1 to 0. Okay, and what is needed is a function in here, and then input a 256 dimensional vector here, and output is 10 dimensional vector, and this is the neural network we called, and we will see how many neural network in the next class. And the neural network will like this. This is our input we see in the above slide, and this is our output. And in the neural network we will have a lot of layers. We call the layer 1 to layer L, and this number is dependent on you. You can set a lot of layers, like maybe you can set this 10 layers or maybe 100 layers, and the result will depend on how many layers you set. And maybe you will say this is 10 and the result is very close to the right answer, and maybe you set it to the 11 or 12, you will get the highest possible answer, and then you get this to the 20 and the possibility will be decreased, and that means you don't know how many layers you need to set is suitable, or you can get the highest possibility percentage answer. So you need to try and get the feedback, and to modify and try and get the feedback, and then you will find the suitable layers in your case. I mean, in every cases the number of layer is variable and it is not fixed. You need to try an error, and then you will get a much close answer. Okay. And this is our image and the output, and we will use this, and it have a lot of function or formula here, and it will calculate by each of nodes in layers, and it will transmit the result to the next layer, and the next layer will do and to give another, and then you can output the result. If you want to know the formula of this one, you can see some AI with mathematical or some basic algorithm, and it will tell you how to count this in mathematics. Okay, this is we can say this is a function set containing the quantitator for the handwrite digital recognition. Okay, we see the real case here. And then we will take a break for 10 minutes, and then we will come back and then see how another video with how the other people explain it, to know the handwrite recognition with the deep learning. We see the real case here first. You can see in this video there are a lot of people to write their handmade number, and the computer will distinguish which number it is. Okay, you can see in this video a lot of people to write their handwrite number, and the system can real time to distinguish which number it is. And then we can see in this step they use a lot of steps to calculate the number and the possible number. Okay, and this is the handwrite digital recognition in the real case, and you can find a lot of other example, and they maybe use different way to distinguish the digital. Okay, and then we take a 10-minute break, and then we will go back here to see the other people explain the handwritten digital number and recognition. And let's have a 10 minutes break. Hope you like this course. Thank you.